Okay, welcome back to week two. We're going to get into our second video here. We worked with factorials and permutations, and now we're going to look at combinations. All right, let's go to the camera. All right, so again, this is week two. We're going to look at combinations. Okay, with permutations, if you remember, order mattered. But combinations, excuse me, the order does not matter. Okay, so again, we're still going to see those little N's and little R's. They still mean the same thing, but you're going to notice there's a C now. Okay, and I had a little typo here. For some reason, this was still in here from permutation, so it was like a leftover. So just cross that out. This is the formula for the combination. So combination is a little different. If you kind of cover this up with your finger, you'll see that that's the formula for permutation, where order does matter, but now we can we are working with combinations where order does not matter. So we just add this extra little tidbit right here. So examples of a combination: creating a committee where order doesn't matter, selecting a subgroup with no distinctions, etc. So let's take a peek. When could we use a combination? Okay, suppose, get these together here. Suppose we want to choose two objects without replacement from three objects: pencil, eraser, and desk. How many ways can this be done if the order of the choices is not relevant and does not matter? So in that case, we're going to break out our old trusty friend, the combination. So the combination formula is right here. If order doesn't matter, it's not relevant, we use combinations. If order matters, remember, it's a permutation. So essentially, we're just going to be asked how many ways there are of choosing two objects without replacement from the three objects if the order of the choices is not relevant or does not matter. So we have three objects, and we've asked to choose two of the objects. So it's a three combination two. Okay, so we're going to use this formula. Let's go for it. So we've got our formula right here. I'm just going to draw a line here. So up top is n. So we know n is 3. So 3 factorial. In the basement, we have n minus r. Here's your n, here's your r. But the extra step we're going to go is we're going to put that r again here. Just like that. Okay, so we have 3 factorial over 3 minus 2, which is 1 factorial times 2 factorial. Okay, so we've got 3 times 2 times 1 over 1 times 2 times 1. And you can see that the 2's and the 1's are going to cancel. And we're left with just 3 over 1, which is really just 3 ways that we could choose two objects from pencil, eraser, and desk. So we're going to choose two objects from the three objects without replacement, and we don't care what order it is. So that's a combination. It's a little different, but you're going to master this very quickly. So I want you to pause this video and practice this combination. Just gave you just a plain one to practice with. Okay, so if you're back, we're going to do 10 factorial up top. That's going to be our, this is our n, this is our r. Okay, then we have 10 minus 3 in the basement factorial, and then you're going to bring that 3 back one more time. Okay, so now, whoopsie, I forgot to put a little parenthesis there. So let's just simplify this. 10 factorial, 10 minus 3 is 7 factorial, times 3 factorial, and now it's on like Donkey Kong. Okay, so when they start getting kind of long like this, notice I started my 7 factorial here underneath where 7 started here, so that you can kind of, it's give an easier time of doing your canceling, which I love the canceling. So we're up to 10 times 9 times 8 up top. Over, it looks like 3 times 2 times 1. Let's figure out what that is. So I got 720 up top divided by 6. Let's cut that into 6 pieces. And that leaves us 120 over 1, or just 120 combinations. So we would have 10 objects. We don't know what objects they are. They didn't tell us. And we are going to choose them 3 at a time. And the order doesn't matter. Combinations are free to do what they want. Don't care about order. All right, try this one. So pause the video. Okay, so this one might seem a little tricky. We've got 5 factorial up top. 5 minus 5 is 0 factorial times 5 factorial. Okay, that might be kind of weird. So what do we know about 0 factorial? We know from the very beginning in the first video and from our first few slides that 0 factorial is equal to 1. So that's really a 1. So you're really looking at 5 times 4 times 3 times 2 times 1 over 1 times 5 times 4 times 3 times 2 times 1. And you can kind of see, what's going to happen here if you already did this. We're just going to end up with 1 over 1, which is really just 1. So we can only do that one way. So we're choosing, we have 5 objects and we're going to choose them 5 at a time. And there's really only one way to do that. Okay, helpful key. If the order of the objects matters or is relevant, we use permutations. If the order does not matter or is not relevant, we use combinations. Here's how I remember this if I'm taking a test. So C, for me, in my brain, I have it as change, and O is order. So change order for that CO. So I'm allowed to change the order here. Can't do it there. So hopefully that helps. Okay, so let's get into some problems that you will see in your homework. Suppose we want to choose 2 colors without replacement from 5 colors: red, blue, green, purple, and yellow. How many ways can this be done if the order of the choices matters? Ding, ding, ding. Okay. How many ways can this be done if the order of the choices does not matter? Okay, so if you're allowed to change order, that's a combination. And if the order matters, we know we're going to permute. That's a permutation. Okay, so I put the little helpful key here. So you're going to have to go back and find your formula for permutation and combination. You'll probably practice this so much they'll be memorized. Okay, so the first one is we have 5 objects and we're going to permute them. We're going to choose them 2 at a time. The other one is 5 combination 2. So 5 objects, we're going to combine them or use a combination to choose 2 at a time. Okay, so 5 permute 2, we've got the formula just says we're going to use that 5, and then we're going to subtract the n minus the r here. Remember, with combinations, there's got that extra step there. All right, so pause the video and get these done and come back and check in with me. Okay, so if you're back for the permutation, I got 20 ways we could do this. Combination, haven't finished that one yet. You're probably ahead of me by now. All right, so if the order matters, if it's relevant, we use permutations. So we're going to get 20 ways we can do it. If the order doesn't matter or it's not relevant, we can use combinations, and that's going to give us 10 ways. Okay, let's try another one. Suppose we want to choose 5 letters without replacement from 14 distinct letters. How many ways can this be done if the order of the choices is not relevant? Aha, remember what that's going to be. How many ways can this be done if the order of the choices is relevant? Okay, so they mix things up on us a little bit here. So make sure to read carefully, all right? So they've changed things. Okay, so get these straight again here. So if you are concerned about the objects mattering, we're going to use a permutation. Remember, we've got this little permutation formula. So 14 factorial over 14 minus 5 factorial makes 14 factorial over 9 factorial. You'll start getting to a point where you probably won't even write the 9 down because you'll know that they're all going to cancel. Until you get to that point, I highly recommend that you just keep on writing it out, even though it's kind of a pain in the tuchus. Okay, so this one's 240,240. It's kind of crazy. I had a little typo here. I wrote that wrong, so I just fixed that real quick. But yeah, so 240,240. Now, if we do the combination, you know that all the 9s are going to cancel all the way down. This one, you still have 14 times 13 times 12 times 11 times 10 up top, which we know is 240,240. Down below, 5 times 4 is 20, times 3 is 60, times 2 is 120. So if we take 240,240 divided by 120, we should get 2002 ways. So some of the problems do kind of get some huge answers, so don't be daunted by that. Just take your time. Try not to get frustrated if you can. Okay. So how many different, this is an example of a combination. Let's see why. Okay. How many different size committees of size 4 can be formed from 14 total possible people? So they're not saying anything about order. They're also saying from a collection of 50 store customers, 2 are to be chosen from to receive a special gift. How many groups of 2 customers are possible? So again, they're not saying anything about order mattering, so order doesn't matter. If they don't say anything about that, then we're going to go with the combination all day long. Okay, so start off with this first one. We have 14 total possible people, and we are going to choose committees of size 4. So we will do 14 factorial over 14 minus 4 factorial. I'm going to use my shortcut here. So we know that's 14 over factorial over 10. So 14 times 13 times 12 times 11. And I'm going to stop there because, you know, once you start getting down to the 10, that's all going to cancel. Let me pause real quick because with the combination, I totally forgot you have to put that R there too again. So I was in my haste to try to show you the quickie way to do it. Look at me screwing up. All right, let's try it again. So we still have 14 times 13 times 12 times 11 times 10 all the way down. We still have this makes a 10, 10 all the way down, which we know can cancel, but we still have to deal with this pesky 4. Okay, so let's try to see if I can not screw this up. So 24,024 over, I don't trust myself, so it's also late. It's been a long day. So, okay, we're gonna get 1,001 ways. Okay, to choose committees of size 4 from 14 total possible people, 14 total possible people if order doesn't matter. Okay, so let's say we've got 50 store customers, 2 are to be chosen to receive a special gift. How many groups of 2 customers are possible? You're probably already thinking about this. 50 factorial over 50 minus 2 factorial times 2 factorial. All right, here we go again. 50 over, what's that? 48 factorial times 2 factorial. So I'm glad we don't have to write this one out. 50 times 49 times 48. So think about that. 48 dot dot dot. That's going to all cancel, but we still have that pesky 2 times 1. Okay, so we are going to go 50 times 49, that's going to be our numerator of 2400, I think. Whoopsie, 50 times 49 would be helpful. 2450 over 2. So let's cut that in half, and I'm getting 1225. So hopefully you pause the video and you should be getting hopefully the same thing I'm getting, which will mean that you're going to get the right answers when you hit that ALEKS homework. Okay, you'll know how to attack. Okay, 3 more problems, and that's it for this video. Let's see what we got. Okay, a catering service offers 5 appetizers, 7 main courses, and 8 desserts. A customer is to select 3 appetizers, 4 main courses, and 3 desserts for a banquet. And how many ways can this be done? Okay, so this is slightly trickier than the ones we've been doing. There's a little more things going on here. So back in week 1, we learned about the fundamental counting principle, where we know, let's say you're going on a trip and you had 3 t-shirts, 2 hats, and a pair of pants. So you can multiply all those together and figure out how many combinations of outfits you can wear. So we're going to need to apply that same principle here. So I'm going to write this out. So first, what we're going to do, okay, we know it's a combination. So we have 3 different things going on here within this combination. So let's start off with the appetizer. They can select 3 appetizers, okay, but they have 5 to choose from. So we have 5 choose 3 for appetizers. So that's 5 appetizers. We're going to choose 3. 4 main courses. So we have, we're going to choose 4, but we can pick from 7. So 7 choose 4. And desserts, we have 8. We're going to pick 3. Excuse me. We have 8 desserts, and we're going to choose 3. Okay, so notice you have 5, 7, and 8. Those are like the totals. So 5, 7, and 8 total numbers of desserts and appetizers and main courses. And then you're choosing 3, 4, and 3. Okay, so we're going to start off with that. Once we get through these combinations, we will apply the fundamental counting principle and just multiply all the answers to these 3. All right, so at the end, let me put a little box down here. We're going to multiply the appetizers times the main times the desserts. Okay, so we're going to go at this. We're going to tackle this with, we'll start with this one here. So 5 factorial over, and I'm going to shortcut this now because you should have be thinking about those formulas and should have them somewhat secured in your brain. So 5 minus 3 is 2 factorial times 3 factorial. So 5 times 4 times 3 times 2 times 1. 3 times 2 times 1, and 2 times 1. We know this cancels. So we end up with 20 over 2, which is 10. So I'm going to put that in my box here. So I know I have 10 ways for appetizers. So I put that down in my little box. Then let's look at the main. So we have 7 factorial over, now 7 minus 4, is 3 factorial times 4 factorial. That's this. So 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 times 3 times 2 times 1. 3 times 2 times 1. Cancel, 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 cancel. So 7 times 6 times 5 is 210 over 6. 210 divided by 6 is 35 ways that we could choose those mains. So I'm going to put 35 here. So this is a crazy problem because we have to do 3 different combinations, and at the end, take those combinations and multiply them together using that fundamental counting principle. So we have 8 over 8 minus 3 is 5 factorial, 3 factorial. So we have 8 times 7 times 6 is 336 over 6, and that's going to give us 56. So that's going to come down here. 56 ways of choosing those desserts, which makes sense. There's more ways there because there's more desserts to choose from. So the final step you'll have to do after you get through that is multiply the 10 times the 35 times the 56, and we should get 19,000. Look at the glare on that thing, 600. 19,600 ways this could be done. That is a lot of combinations. Okay. There are 10 acts in a talent show. An acrobat, a comedian, dancer, guitarist, juggler, magician, pianist, singer, violinist, and whistler. A talent show host randomly schedules the 10 acts. Compute the probability, oh, this is different, let's circle that word, that the guitarist is first, the whistler is second, and the singer is third. There's 10 acts, we're interested in scheduling 3 of them. We are, at least for the first, second, and third act, we are asked for the probability of a specific order. What will we use? Okay, specific order hopefully gives birth to, we know now, a permutation. We have to keep in mind that they're working with probability here, so we're going to have to deal with that at the bitter end. So let's permute. Okay, here we go. So we have 10 acts, and we are going to permute or choose them 3 at a time. The order matters because they are being specific. The guitarist has to be first, the whistler has to be second, and the singer has to be third. So we're going to permute, which is my favorite formula because it's the easiest one. You don't have to add that extra R. And then I'm going to shortcut 10 times 9 times 8 times 7. I'm going to stop 7 times dot, dot, dot. All that cancels. We have 10 times 9 times 8, which is 720. Okay, now they ask for the probability that the guitarist is first, the whistler is second, and the singer is third. That's a probability. So we know there's 720 ways, that this could be done if the order matters, the order of the acts matter. But we are going to randomly choose or use one of these 720 permutations. So we started a probability last week, so we know that this probability is going to be 1 out of 720. So when you get to the problems where they start talking about probability, you're still going to go through either your permutation or your combination. But then at the end, step back and think about what they're asking. Compute the probability that this is going to happen. There's 720 ways it could happen. And there's really only one chance out of 720 that it's going to happen that way. Let me think that was the last problem. No, maybe not. This looks very similar though. Let's see here. There were 10 acts in a talent show. Same talent show. A talent show randomly schedules the 10 acts. Okay, compute the probability that the first 3 acts are the acrobat, the violinist, and the dancer. Oh, there it is. In any order. It's a combination. Order doesn't matter. Change order. Okay, so we have 10 acts. We're going to choose 3. Order doesn't matter. So we have our 10 over 10 minus 3 factorial times 3. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 over 10 minus 3 is 7, right? I think it is. So 7 times 6 times 5 times 4 times 3 times 2 times 1. We still have to deal with this pesky 3 times 2 times 1. All of this cancels. So 10 times 9, 90 times 8, 720 over 6. So that's going to leave us 120. All right, ways. Now keep in mind, they use the word probability. So we know we're going to randomly choose. We are going to randomly choose or use only one of the 120 combinations. So it's 1 out of 120. That's the chances. That's the probability that they're asking for. Okay, I hope that these 2 videos have helped you, or they will help you as we navigate through week 2's probability. Keep in mind, we have 2 more weeks of probability, and it starts to get pretty crazy, definitely by week 4. So I'll see you back for that craziness. Bye.